Hello, I'm Satoshi Oshima from Nagoya University. My talk title is Performance Evaluation of Accurate Matrix-Matrix Multiplication on GPU using Sparse Matrix Multiplications. This work is based on the master thesis of the first author, but he is now working in a company, so I introduce this work. This slide shows the background, objective, and motivation of our work. High accuracy and low accuracy calculations are one of the important calculation techniques which can solve large-scale and complicated calculations. Focus on the numerical library. Some studies have investigated the accuracy assurance of Brass and Layback. However, these studies have used mixed procedure computations and arbitrary digit computations. Moreover, most of Brass and Layback libraries tend to place less emphasis on the accuracy of the computation results. One of the reasons why high accuracy and assured calculations are not widespread is computation time. These kind of calculations require a lot of calculation and time. Therefore, we consider to calculate it on GPU and shorten the time. We believe this work will be helpful for large-scale and complicated calculations on current and future generation computers. Our target calculation is assured matrix-matrix multiplication method proposed by Professor Ozaki. In this presentation, I call this method the Ozaki method. This is the overview of the Ozaki method. Let's consider C equal A times B. A, B, and C are matrices with these sizes. The first step is the error-free transformation. In this step, matrix A and B are divided into submatrices. The elements in the matrices with lower indexes are given with a higher number of digits. The second step is the individual matrix-matrix multiplication. The final step is the accurate summation. Each result of the step 2 are summed up by the accurate sum algorithm. This slide shows the example of C equal A times B by double precision, which may cause some errors. If elements of matrix A and matrix B have these elements, first row of A times first column of B is calculated in this way. Then, loss of trailing digits may be happened. On the other hand, in the Ozaki method, each matrix is transformed in this way. Then, individual matrix multiplication is calculated. After that, final result is calculated by accurate summation. In this calculation, both round-off error and loss of trailing digits are not happened. When the value ranges of the input matrix elements are large, error-free transformation generates many sparse matrices. In this case, many double precision general matrix multiplication, this is a DGEM calculation of Brass, are performed. Then, transforming dense matrices into sparse matrices and performing sparse matrix operations will require shorter calculation time than dense matrix operations. Therefore, our previous work proposed to transform the target matrices into sparse matrices and calculate sparse matrix computations on CPU. Because many matrix computation libraries don't provide fast sparse matrix multiplication implementations, multiple sparse matrix vector multiplications are used for computing sparse matrix multiplications. In this study, we propose to calculate these sparse matrix computations on GPU. This slide shows previous method and proposed method. Right side is figure 6 in our paper, and this is our proposed method. But I apologize that the reference number 9 in figure 6 in our paper is incorrect. Number 8 is correct. Our new approach is using GPU. We use two sparse matrix formats in the evaluation. One of them is a CRS format, and another one is an ELL format. Because these formats are famous sparse matrix formats, and they are used in many sparse matrix calculation programs. Then, I don't explain the details of them. Before performance evaluation, I confirm the implementation variations. Because many matrix computation libraries don't support fast sparse matrix multiplication implementations, our previous work used multiple sparse matrix vector multiplications. In this work, we measured the execution time of all implementations in a few cases. Sparse matrix multiplication, multiple sparse matrix vector multiplications, and sparse matrix dense matrix multiplication. Some kind of automatic selection system which can choose the best implementation for each input is desirable. It's a future work. I'll show you the performance evaluation. We used DWH supercomputer system installed at the Information Technology Center, the University of Tokyo. Each node of DWH has 2 Xeon Broadwell EP CPUs and 2 Pascal GPUs. We used Intel compiler and CUDA for development. In this evaluation, all matrix multiplications are performed with double precision. We used one computation node and all 36 cores for CPU computation. On the GPU, we used cuSparse library for matrix computations. Specifically, these cuSparse functions are used for these computations, respectively. This slide shows the information about target matrices. Matrix A is an identity matrix with additional elements. The additional elements are generated by a pseudo-random generator. Matrix B is inverse matrix of A, which is generated by the layback. And we used two matrix sets. In matrix set 1, the sparseness of matrix A is 19%. The sparseness of each submatrix A obtained from the Ozaki method is higher than 19%. All submatrix A, submatrix B multiplications are calculated by SpMV. In this matrix set, execution time of matrix multiplication using CRS format and ELL format and on CPU and on GPU are compared. This means a comparison with previous method and our proposed method. In matrix set 2, the sparseness of matrix B is one of the following 7 types: 90%, 95%, 96%, 97%, 98%, 99%, and a zero matrix with only one element inserted. While matrix A is a dense matrix, it is stored in the CRS format. In this matrix set, execution time of matrix multiplication on GPU using SpMM and SpM are compared. This means a comparison with two implementations in our proposed method. For both matrix sets, matrix sizes, it means both height and width of original dense matrices are 50, 100, 500, 1000, 5000, and 10,000. These tables show the number of matrix divisions by error-free transformation in each matrix sets. Large matrix size is not always required large number of matrix divisions. These sizes depend on the algorithm of the Ozaki method. This slide shows the execution time of accurate matrix multiplication using SpMV in CRS format and ELL format on CPU and GPU for matrix set 1. This evaluation compared the previous method and the proposed method. There are 6 graphs. Each graph includes combinations of CRS, ELL, CPU, and GPU. We can see that when n is small, CPU is faster than GPU, mainly because data transfer between CPU and GPU, the purple parts of GPU in graphs, is not negligible. Moreover, time of launching GPU kernel is also not negligible. In the case of CRS format, GPU is faster than CPU when n is greater than or equal to 1000. In the case of ELL format, GPU is faster than CPU when n is equal to 10,000. The maximum speed up ratio from CPU to GPU is 3.24 in CRS format and 2.03 in ELL format. Next slide shows the execution time of accurate matrix multiplication using SpMM and SpM in CRS format on GPU for matrix set 2. This evaluation compares the two implementations of our proposed method. This page shows the smallest two cases. I apologize that the labels of figures from 13 to 18 of the paper are incorrect. SpMM and SpM are interchanged. In the case of SpMM, because matrix B is dense, time and sparseness have few relationship. If the sparseness is very high, execution time is not shortened. On the other hand, in the case of SpM, when n and sparseness increase, it is expected that calculation time is relatively shortened. When n is small, time of the memory management of matrix B and C, which includes data transfer from CPU to GPU, is dominant at all cases. And execution time of SpMM are smaller than time of SpM. But when n is large enough, execution time of SpM becomes short. In the case of n equal 10,000, SpM beats the SpMM when sparseness is 99% and max. This percentage is not very rare in the large-scale simulations. The maximum speed-up ratio from SpMM to SpM is 8.44. This is a conclusion slide. we propose to calculate sparse matrix calculations generated by the Ozaki method on GPU. Our performance evaluation indicated that, compared with previous work using CPU, performance improved by using GPU when the input matrix is large. We showed that accurate matrix-matrix multiplication using SpMV in CRS format on GPU achieved 3.24 times higher performance than on CPU, and SpMV in ELL format on GPU achieved 2.03 times higher performance than on CPU. We also showed SPM implementation is more effective than SpMV implementation when matrix B is highly sparse. We showed that accurate matrix-matrix multiplication on GPU in CRS format using SpM achieved 8.44 times higher performance than using SpMM. These results show that our proposed method is effective. While we confirm that our proposed method is effective, there are some complicated conditions, such as matrix format, matrix size, and the sparseness. To utilize our method effectively, it's important to analyze the relationships between optimization parameters and performance. To apply auto-tuning technology and to make using our proposed method easy are our important future work. My talk is over. Thank you for watching.